Next, we look at the free body diagram for our box in the elevator. Again, our box is just going to be represented by a dot. We have gravitational force acting down, normal force acting up, and a net force. That's what we get when we add this to this. What about the relative proportions of our vectors? Well, what are we given? Our net force, our acceleration, is going to be 1.4 meters per second squared downward. So that our net force is our, whatever the mass of our box is, multiplied by negative 1.4 meters per second squared. Okay? So we want to express our net force. We aren't given a mass, so we invoke a mass. We just call it whatever the mass is. Got to have mass. We'll just call it big M. Positive direction is taken as upward, making the acceleration, the downward acceleration, negative. Okay? Then we have the gravitational force, which is, again, the mass of the box, times the gravitational acceleration, which, positive direction being up, is negative 9.8 meters per second squared. Now, we put this net force in proportion to the gravitational force, or vice versa. 9.8 is 7 times as big as 1.4. So the gravitational force vector has to be 7 times as long as our net force vector if we're going to make a picture that's pretty representative of the situation. Now, we don't have to take rulers and straight edges and do everything, measure everything out to scale. We're just doing a rough diagram, but we do want to keep these things in reasonable proportion. So it wouldn't make any sense for the force vector to be this long and the gravitational vector to be this long, because there's a lot of difference between 1.4 and 9.8. There's a big ratio. 9.8 is several times as big as 1.4. Gravitational vector has to be several times as big as the net force vector. Okay, well, then we also have, since the box is not accelerating downward at 9.8 meters per second squared, we got to have some force acting upward to mitigate most of that gravitational force, and that's going to be the normal force between the floor of the elevator and the box. I'll comment that a lot of people in drawing this tried to draw the elevator and the tension in the cord supporting the elevator. In one sense, that's really good. You're thinking about everything that's going on, but when it comes down to it, you just isolate the box and you don't worry about what it is that's holding the elevator back. Maybe the elevator has some thrusters, burning down. Probably wouldn't be very convenient in a closed elevator shaft, but maybe. Okay. Now, what's the relationship here? We know this acceleration. We know this acceleration. We don't know what the normal force is, but we can write our net force equation. Net force is the sum of these two forces, the gravitational force and the normal force, which seems to be missing the arrow over the top of it. Okay. The only one we don't have an expression for is the normal force, so we'll subtract the gravitational force from both sides. So now we have net force minus gravitational force, and I've kind of got the calculation here. That's mass times negative 1.4 meters per second minus the mass times negative 9.8 meters per second squared. Okay. Subtracting a negative means we're going to add mass times 9.8 meters per second squared to the mass times negative 1.4 meters per second squared, giving us mass times 8.4 meters per second squared. Okay, so now we determine that this is whatever the mass is times the 8.4 meters per second squared is upward. Adding that to the gravitational force does give us the net force.